Hi there, welcome back to the channel. Welcome to a new project. Now, you might ask, what does a box from PCBWay with some boards on top have to do with a Simpson 260 analog multimeter, a Bryman digital multimeter, and one of these little things with two pots on there? Well, you may ask, and I will tell you. It's got to do with me wanting to make that into that, but not losing that. Okay? Does that make sense? I want to achieve the sort of precision that I get from the digital multimeter on my analog multimeter with an analog scale, and I want to be able to do that without having to give up on the advantage of the analog scale. And the fact that there's a PCBWay box here is because that's what the latest boards came in, and they sponsored the video, so I want to thank them for that. Let me show you what I'm talking about. What I've got here are two pots, and I'm going to use these as potential dividers because I'm going to be measuring some voltages that are part of the maximum voltage across here. I'll explain that easily enough. I'll put the negative of the power supply, the bench power supply, on there, and I'm going to put the positive to there, which means that when I switch on the bench power supply, like I've done now, I've got, 3 volts across there. 3 volts from the bottom of the pot to the top of the pot. So 3 volts across the potentiometer. Now, if I measure that from the wiper, so I'm putting this to the ground and the positive to the wiper, you see that I can adjust it, right? All the way to close on 3 volts. All the way down to pretty close to 0, okay? Now let me put that on 1 volt. Close enough, right? Now I'm going to connect my Simpson to the same place. This gets a bit messy with lots of wires, but you'll get the idea. Look at that. What the hell happened there? Well, this has got to do with the input impedance of this meter. This spot over here is a 250 kilo ohm linear potentiometer, and I can still do this, and it still goes up to 3 volts. This is set to the 2.5 volt range. That's why it went over the top. But as I get down here, if I measure that position there and I take the analog multimeter out, it goes up, okay? Because what's happening is the input impedance of this is 20k per volt. So on 2 volts, 2.5 volt range, which is what the minimum range is here, it's about 50 kilo ohm impedance in there. I'm putting 50 kilo ohm in parallel with part of a wiper or part of a pot. So I'm changing the whole configuration here. The potential divider also uses that impedance. Now the impedance of the digital meter is about, I think, 10 mega ohm. So it doesn't really affect it because it's much, much, much higher than that. But that thing is very low. That is a problem with analog multimeters, okay? Now, if I change this, there's 0.6. If I change this to 10 volts per division, it goes up. If I change it to 25 volts per division, it goes up again. If I change it to 50 volts, it goes up again. So obviously you can't even see that there anymore, but the input impedance here has been going up at 20 kilo ohm per volt. So this resistance at, say, 50 volts is 1 meg. And 1 meg is much, much greater than 250k of the pot. So that's why I'm getting that reading. And if I take this out completely, okay, there is still a change, but it's not that big, all right? There we go. So that is the problem with these multimeters. There are a lot of advantages with this, and that's why I want to do this project. But this is one of the disadvantages. The other disadvantage is that if I take this to a smaller value pot, and this one here is 2K, is going to be set to 2.5 volts. And I'm going to put that across there as well. And it comes down a little bit. Now, why is that? And that's pretty close to that reading. This meter is pretty accurate. It's pretty well calibrated. And it's pretty close to that reading. But what is going on here? Well, the reason is that this 50K is now much greater than the 2K pot. So it represents a fairly high input impedance compared to what this thing is rated for. So again, I don't get as much of an effect. It still affects it. If I take this out, it still goes up, but it's not that much. So again, my problem is the input impedance of that multimeter is too low. What I would like is to make this input impedance much, much higher. And it is indeed much, much higher when I go to the higher voltage ranges. But what I want this for is for low voltages, especially very low voltages. Because watch this. If I leave it on there and I'm going down to 0.5 volts, call it 0.5 volts, all right? Look at that meter. It's sort of down here. It's sort of, I can sort of read it, okay? I can sort of read it. But if I go even lower to 0.1 volts, well, there it's at 0.3 volts. Yeah, it is at 0.3 volts, probably. I can't even see. I have to go and check this thing. It's moving around because this thing's got probably not a new pot. It's an old pot. I know it's not a new pot. But it's very difficult to read down there. This range of 2.5 volts is too high for this type of voltage that I want to read. And recently I had a problem where I was aligning that Sony radio, and it had me measuring voltages to peak certain parts of the circuit. And the problem was the voltages were somewhere down here. I wanted the analog movement so I could peak it properly, but it was not, for example, there or there where I'd be able to see it clearly and where it would be a lot easier to make the alignment. So what I decided to do was to design this thing. Now this thing is called Electronics Old and New Voltage Multiplier. Well, all it is a device that I put between the probes and the analog multimeter at the back there to multiply the voltage, the input voltage, by an amount that I can control with a couple of dip switches here. In other words, I'm going to amplify that signal, but I'm also going to represent or present a much higher input impedance than this thing would, because the output of this then goes to the multimeter. So let's say I've got 0.1 volts, a reading in the range of 0.1 volts, and I want to use this, to peak it, because I like that. Then what I do is I feed it in here, I multiply it by 10, and now it's on about 1 volt. On the 2.5 volt range, I would still like it to be better, but it's about there. This pot is really bad. It's about there, so that's readable, okay? 0.1 volt is not, it's way down there. I can't even see it. And it is on the lowest range. So I'm going to be able to multiply, and I've made this thing so that I can multiply by, the minimum is times 2, then I'm going to make it times 5, and then times 10. So I can click a couple of dip switches and adjust the amount of multiplication that I put in. Now, is this thing absolutely accurate? No. Does it have to be for my purposes? No. It's fairly accurate. Yep, it's fairly accurate. You can calibrate it to be very, very accurate, but I don't really worry too much about the precision. I'm worrying about the alterations that I'm able to see with a moving coil meter like that, which I cannot do with the digital one. So let me show you the schematic for this. It's very, very simple. It uses 1 quad op amp. It's going to run off a 9-volt battery. I've also gone and 3D printed a case. When you've got a 3D printer, you find any excuse to use it. It's going to have a couple of banana sockets there. So the 2 there will go to the measuring point, and those 2 there will go to the meter. And this thing will fit inside, and it'll have the dip switches sticking out. It'll have the battery in here. Let me show you the schematic, and we'll take it from there. Here's our schematic. Pretty simple, because I want to use a 9-volt battery. So this is the 0 volts of the battery, 9 volts of the battery. That comes in here, that becomes my V minus. The positive goes through an on-off switch. I use this because I need the 2 contacts or the 2 solder tags on the board instead of using a symbol. Switching on the supply to that point over there, I call that V plus. 2 resistors, this thing creates 4.5 volts in the middle here. There's a little smoothing capacitor here just to keep it stable. There's obviously a little LED with its resistor on here just to light up and tell me that I've switched it on. And I've got 4.5 volts going into this non-inverting input of this of the op amp, one of the op amps in the op amp package. This is just a follower, so I get 4.5 volts over there, reference to my V minus. In other words, I can call that ground, 0 volts. I'll have minus 4.5 plus 4.5. Very simple. That's the best way to make a virtual ground from a 9-volt battery that I know of. I've also got two capacitors here between V minus and ground and V plus and ground. These are 0.1 microfarad. They're here because I need positions for them on the board to decouple the IC power supply pins. So that's done. So what we've got now is we've got plus 4.5, minus 4.5 and ground that these three op amps will see. The first one is used as your probes. So you measure with the two probes over here. There is a 4.7 meg, you can put 2.2 meg, you can put in 1 meg. The higher you put here, the less loading it will have on your measurement. However, it also can allow more noise to come in, so you can play around with that. I've actually put a 1 meg on my board that I've built, and I'll show you in a second, but I'll probably raise that to about 2.2 meg. And so our input signal comes in here. Now remember, we are measuring small voltages. The whole point of this is because we want to improve the impedance, the input impedance of that analog meter at low voltages, because it's low volts times so much K per volt, it's low input impedance. I can't use this at very high voltages, obviously, because the maximum that I have here is plus 4.5, minus 4.5. Never forget that, okay? So I've got two diodes on here, which means that if this voltage over here is higher than 4.5 plus of diode drop than that one, it'll start conducting. So it won't blow the input of this op amp, which it could do, okay? So my signal comes into the non-inverting input of the op amp, and it is simply unity gain buffered. So the signal coming in here is now over here, unchanged, hopefully. And now we've got another op amp configured as a non-inverting amplifier. So the signal goes into the positive. And now the gain of this op amp is 1 plus this resistor divided by this resistor. If you ignore this, if you take these guys out of the equation, you have a gain of 1 plus 10K divided by 10K, which is 1, which means 1 plus 1 is 2. So the gain of this stage would be 2 if both of these guys were off. So the minimum gain that my system gives me is 2. If I have this, both of these off, I get a gain of 2. So it doubles the amplitude of that signal. Now remember, what you're seeing here is directly coupled everything, right? So this could be AC volts or DC volts. No problem. It's working for both. Now, what happens if I start bringing these resistors in? Well, this 10K is fixed to ground, and whatever resistor I switch in over here is going to go in parallel with that one. And I want to put a resistor in here, for example, in position 1, which, when activated, gives me a gain of 5. In other words, whatever I put on here is going to go in parallel with that. It's going to drop the total resistance of this leg. So this will be 4 times that, right? 1 plus that divided by that is 5. That means this total sum here, or the result of this network, should be 2.5K. 10 divided by 2.5 is 4 plus 1, 5. So that's an amplification of 5. When I switch that off and switch that on, I want this to multiply by 10. So again, same story. That'll be, 9 times less than that. But what I'm going to do is I'm going to use some trim pots, and I'll show you that when I build it. And then we can replace it with fixed resistors. It's easy to work out, but it's actually easier just to demonstrate it. So times 5 or times 10, depending on the amplitude of the input signal that I've got. And then what I'm doing here is just unity gain buffering it again, because I've got a spare op amp in the quad op amp package, and that now goes to my meter. I've actually put a 100 ohm resistor. I like doing this on the output of op amps because if you've got leads and all that, you don't want oscillation. And I've just put a 100K resistor on there as well, just to give it a ground reference. That shouldn't be a problem because my input impedance is 50. Will it be a problem? I may actually have to raise that. We'll see what happens when I put it up. All right, let's go and build this thing. So here we are. And because I love showing you every single solder connection, I'm going to be soldering this one leg at a time. I prefer this. I've already done it, and this is the result. I've got the IC on a socket in case I want to replace it. This is a TL074. The TL series is one of my go-to series because it's a FET input op amp. They're very high impedance. So TL074, everything else is standard. And I have used 2 trim pots here in the position of those X and Y resistors. so that I can adjust the gain. Input over here, output over there, the switch, these will be soldered to the switch, and my battery connector, okay? And on the other side, which will be facing the top, is my dip switches. So I've got 1, 2, so I can have 1 on, or I can have 2 on, or I can have both off. And indeed, I've got one more gain setting, which I think comes out about 14 times, which is when I have both of them on. But we'll see that when we test it. So this is it. This is all it is. And now I can fit this in my 3D printed box. Hopefully it'll fit quite well. I can actually fit it and then make the adjustments, but I'm going to do some testing outside just to do the calibration of these pots. I might even leave these pots in there because I might want higher gains. I'm not sure. These trim pots are fairly small. They'll fit nicely in the case. I might not even take them out. I might leave them in. But let me connect a signal to here. I'm going to use an AC signal, and we'll be adjusting gains accordingly so that we can get what we want from here. I'll start off with the 0, 0, okay? Let me connect it up and show you the result. All right, what I've got here is I've got a 100 millivolt signal coming in, low frequency. I think it's about 600 hertz or so. I'm testing this on AC, so I've got my multimeter on AC volts to the output. My switch is still off. I will switch it on by doing it like this. The LED is not really soldered in because I need to solder it at the right height when I put it into the little enclosure. But what I've got now is 0.2. And if I increase the amplitude of the input signal to 200 millivolts, I get 0.4, 300 millivolts, 0.6, and so on, okay? Let's go back to 0.1. Now I'm going to change this by clicking on one of these. I'll click on 1, and 1 is adjusted with this trim pot over here, and I want 5 times. Wrong way. So 0.1 has become 0.5. That's accurate enough for me. Let me try on 0.2 volts input, 1 volt output, 0.3, 1.5. Yeah, it's good enough. Now this other one adjusts the 10 times. It's a little too high. These are 10-turn pots. There we go. 100 millivolts is now 1 volt. And if I go to 0.2 volts, that's 2 volts. That is pretty good. Now I can also go one step further and I can make both of them active. And I get, it's easier to do it on 0.1, I get 13 times. It just means that those two are now in parallel with that 10K resistor on the output. And that's really all it is. So if I'm measuring something in the region of, let's say 0.1 volts, I can simply, if I want some sort of accuracy, I can put just 2 on, and I'm going to get 1 volt, and that's going to become read. That's going to be read by this output here to the analog meter. I'm only using this to calibrate, and it will make it more readable. If I want it even higher, I just click both of them on. Actually, I have to switch both of them off. And I get, here we go, 13 times. You get the picture, right? So what I'm going to do now is I'm going to put this in the enclosure, put the banana plugs and all that sort of thing in there and show you the final result, and we'll test it on the analog meter. I like it. I like it. I like it a lot. This thing is going to become very useful because I love that Simpson. The other one that I've got is the Avometer 8, which the lowest range for that is, I think, 3 volts. 3 volts DC. So it's got the same problem. This will be useful on that as well. Okay, next step, enclosure. And here we are, folks. It's all in. Input, output, dip switch. It's now set on 0, 0. Power LED there's a switch on the side there. And if you look inside, this is what it fits like. The switch is over there. The battery, I've left the leads long because I don't need to cut them. I can just bend them in here. This took a while to actually design and print. Every time you try and print and get it wrong, it takes about 5 hours to print it again. But I finally got it done, and now it's got a lid that goes on here. And I've got engraved text in there that I then painted in with that acrylic paint. These screws stick out a bit, so I'll have to put some feet on, otherwise it'll wobble. But that's what comes from experimenting. You try again, and you finally get it done. So, multiplier. 0, 0 is times 2, 0, 1 is times 5, 1, 0 is times 10. And this is what that means. 0, 0, 0, 1, 1, 0, and 1, 1, if I want to try that. So now all I need to do is actually connect this up with that multimeter again, with the Simpson, and see that it's working. I'll try it with DC voltages, because that's the... I've done the calibrating with AC. I'm going to try it with DC voltages, see what we get. Right, here we are. I've got this connected to the ground and the wiper of the volume of that potentiometer. This is going to my Simpson. That mess there's the potentiometer and all the cables connected. You can see the voltage actually being measured at the back, 0.34377 volts. Let's call that 4 volts. I've got this on, let's put this on 0, 0. So 0.4, I should have 0.8. And on the 2.5 volt range, where are we? It's actually reading 0.75. Not bad, okay? But if I have an alteration there, I can see it, although it's still not the kind of sweep that I would like. So I'm going to multiply by 5. And in that case, I just flick number 1. And now I've got 2 volts, pretty close to 2 volts over there. And if I alter this now, I'm actually altering between 0 volts and 0.4 volts. And there's my range on the 2.5 volt range. So I know that this is 5 times less than what it's actually measuring, but it's doing a good job. Now, if I want to look at this, if it's slightly higher than that, I could put this on the 10 volt range. And I've got times 5, but I can also give it times 10, which means it goes up to 4 volts. Pretty close. Now, watch that voltage when I remove this metering, okay? This is the load on there. See that? It hasn't affected it at all. This thing has swung because it's got no ground reference on the input, but you can see that it doesn't really affect that reading at all. This load is high enough, this impedance is high enough that it doesn't affect my circuit at all. And that, my friends, is what's going to make my Simpson and my Avometer that much more useful. You see here I've got AC volts. The maximum is 3. DC volts, the minimum rather is 3. DC volts, minimum is also 3. So again, I've got the same problem with this meter. Admittedly, I use that one most, but this will apply to any multimeter where I want to increase the input impedance for low voltages in order to be able to measure a better resolution with the scales that they come with. And as I mentioned, if you've got something stable and you want absolute precision, you're going to use that, all right? If you want to see alterations and you want to peak things and you're working with low voltages, these are the best. That one's my favorite. And that's what I use most of the time anyway. So that is my multiplier. I still haven't done the thumbnail, so I still am not sure what I'm going to call it. Over here, I called it the multiplier. I don't know if that's what I'm going to call it. Maybe you've got better ideas, but I'll call it the AC-DC voltage multiplier. For now, it's a working title. But the project is done. And this is going to be on my bench to be used just about any time I'm doing low voltage adjustments with my moving coil meters. All right. Hope you've enjoyed that. And I'll be putting these boards up on the PCBWay website share section. I'll put the link in the description below if you want to order some yourself. And if you've enjoyed that, don't forget to click like, share, subscribe, and all that jazz. Thanks for watching. Bye for now, and stay safe.